Hey folks, this lecture is going to be about section 17.5. It's called Divergence and Curl, but in particular, we've actually seen these things in 2 dimensions, so we're looking at it in 3D now. I believe I already introduced this thing, the del operator. It's pronounced del. Sometimes I look at that and I say grad just as often as I say del, I think. But technically it's supposed to be del. The reason that sometimes I make that mistake is we used del originally to make the gradient of a function. So, but what del actually is a strange little entity. It's a vector, kinda. It's a triple of operations, not a triple of numbers or functions. It's 3 partial differentiation operators stuck together into a vector. And I think del is a great example of what in math they call abusive notation. That's really not a vector, because you should have things that amount to numerical quantities in the components of a vector. But it turns out that treating it as if it were a vector, you get the same you get the very results you would like to get. So yeah, the only thing that's weird about this notation is you have to remember that multiplication with the components of del means apply the operator. So the first example we got of using del was to make gradients. I already said that. So if you have a function f, when you write del f, that's really a vector times a scalar. So that is, it's the vector. I'm going to start using this shorthand that I think I also introduced you to previously. You can just write partial x to mean partial over partial x. That's also an abusive notation, but whatever. It'll save us some writing. So partial x, partial y, partial z, those are the components of del, and then we've got our function f. And so when you have a vector multiplied times a scalar, you distribute the scalar in. And so you get partial with respect. Sorry, I said I was using the other notation and then I started to not. Partial x times f, partial y. Did I fix that? Yeah, that's mostly fixed. Times f, and then partial z times f. So we get a vector of things, and it's probably better to write this in that more compact notation where you say you get f sub x, f sub y, and f sub z. So you see where the multiplication means apply the operator happened? It was from this step to here. Partial x times f means actually get the x partial of f. Do the operation to f. Well, the next thing to do is to try to use del in dot products and cross products. And when we do that, we're going to respectively get the divergence and the curl. So let's look at that. What would it mean to take del dotted with something? Well, first of all, if that's going to be a dot product, the something here had better be a vector field, right? So let's change that. That's del dotted with a vector field. What does it mean? Well, the del operator is this thing with partial differentiation operators in it. That is, it's a vector with these partial differentiation operators. And f, well, typically we write f as having these component functions, f, g, and h. And I'm dotting those things. So, excuse me. So when you do the dot product, you multiply corresponding things and add them up. Just formally, we get partial x times f plus partial y times g plus partial z times h. I was about to write a vector brace on the end of it, but that would be wrong, right? Because when we do the dot product of two vectors, we get a scalar. So now we'll do the part where it says multiplications turn into just apply the operation. So we'll get that the x derivative of f plus the y derivative of g plus the z derivative of h. Now, that is really just one extra component to what we did in the two-dimensional version we saw in Green's theorem. This piece, fx plus gy, that was from Green's theorem. Which version of that is it? The one where the line integral has the normal vector, and this is the so-called two-dimensional divergence. When you add in the third component, you've got, so I think that's fairly straightforward. What happened in Green's, you're just adding the z coordinate in to get the divergence in the more general case. Or I suppose you can think of that in reverse, that if you have a three-dimensional thing, you can just truncate it, like leave off the h sub z, and you've got the 2D version for Green's theorem. All right, well, one more trick to do, which is think about the last remaining vector operation. Can we form a cross product of del with a vector field? I'm thinking I can do this just with my eraser. Yeah, turn that dot there into a cross. I don't quite have room for the cross in here. That's going to look weird, but okay, close enough. So, well, what does that look like? You do the cross product business. I think I'm going to have to stretch it out a little bit so we have room for things. All right, the first vector is the del thing, so partial x, partial y, and partial z go into that second row. And then the component functions of our vector field, f, g, and h, go into the third row. We've done a million cross products by this point, so the only weirdness now is that when we do a product, it's actually going to be like partial x times g. That's going to be take the x derivative of g. I don't know why I pointed that one first. The first one I want is this one. Take the y derivative of h. So you get h sub y minus g sub z. Okay. That's from I times that x, and then j times this x, f sub z minus h sub x. And last but not least, when we get the k component, it's this x, right? Partial x of g, g sub x, minus partial y of f, f sub y. And you should notice, and I think I actually did already point this out, this piece right here on the end, that's the Green's theorem thing. That's the thing it's the k component of what this thing is called the curl of the vector. So, actually, now that I've used the term, I should probably write it down. When we take the del operator and we dot it with a vector field, we get a thing called the divergence of the field. And when we cross it with the field, we get a thing called the curl of the field. Just some definitions. Divergence of a field f is equal to del dotted with f. The curl of the field f, that's del crossed with f. I'm going to put this to use in a couple of interesting calculations. There's actually, let me grab the board and start fresh. A radial vector field is a vector field that basically looks like you can compute it from the position vectors. So if you think about a position vector r, you just take r and scale it by something. Typically what people use is powers of r's own length. So take the vector r and divide it out by its length to some power p. A special case of that is when, for instance, p is equal to 1, then you just have unit vectors that are pointing away from the origin. P equals 1 would look kind of like this. Vectors that are all unit length, no matter where you are. Even if you're in really close to the origin, they're unit length. If you're really far from the origin, they're unit length. So length 1 vectors just point out, away from the center. That's p equal 1. P equals 2 is sort of an interesting one too. Actually, the other value that I should probably mention is p equals 0, which just means you're dividing by 1, or in other words, you're really not even dividing. P equals 0, the vector field is equal to the position vectors. And this is the field that occasionally I've pointed out to you looks like an explosion. When you're in close to the origin, you have teeny tiny vectors pointing away from the origin. When you're farther away, you have much larger vectors. In fact, and they point straight away from the origin. The length of the vector is actually itself. It's the position of its tail. So if I'm out here, I would have a vector that went right off the board because it would be this long. So anyway, the vectors get longer as you go away from the center. That's the idea. There's a pretty good 3D graphic of this explosion vector field in the book. Oh, that's not long enough. It needs to be more like that. Yeah. I hope you get the sense of it. P equals 1 gives you a bunch of unit vectors. P equals 0 gives you vectors that are getting longer and longer. The bigger values of P get you vectors that are spreading away from the origin, but they're not growing larger like this. They're getting here they were always the same length. If you make P2, they're getting shorter. So that's a kind of a nicer vector field. It's got a little issue that happens right at the origin, though. Because when the vector r is 0 in length, you raise it to the pth power, it's still 0 in length, and you're dividing by 0 there. So if p, I guess we're having that issue with this one as well, but not with this one, because 0 to the 0, well, we can take a limit anyway and just call it a 0 vector there. So that's just a quick intuitive look at what these radial vector fields are like. Let's take a look at the divergence of one. There's a really interesting formula that is this. If you take del dotted with a vector field f, as we just defined it, you get 3 minus the power divided by r to the p. Just checking my notes. Yep, that's right. 3 minus p divided by r to the p, which is pretty amazing that you get this thing. It tells you something about when is the divergence 0. When would the numerator of this be 0? Right, when p is 3. So if you have a vector divided by its length to the third power, you have a divergence-free field. It has no divergence. Any other time, you're going to have divergence. If you have the, let's see, if p is bigger than 3, you're going to have negative something here. So you'll have negative divergence. That's weird. And if p is less than 3, you'll have positive divergence. So I should mention something that people use to talk about divergence, or use to think about divergence. They're called sinks and sources. And if you have single points that behave like a sink, they look like this. The vectors are all heading in towards them. So it looks like the drain in your kitchen sink. You know, the water is all heading towards the drain when you pull the plug. Sources are sort of that in reverse. A source would be something where you'd see vectors flowing away from that. All the vectors in the field might go out like that. And you know, these things, you see them in the real world, in electrostatics, for instance. I'm not sure which direction we think of it as, but you know, a positive charge might be thought of as the lines going towards it, a negative charge, the lines going away from it. And really these lines, you know, are continuous from one side to the other. You get a field between two charged particles. Similar thing if you think about a north and the south pole of a magnet. You get these lines of force, they call them. But you don't have to have individual points that are behaving as sinks and sources, and that's a little bit harder to imagine. But you know, if you had a whole lot of tiny little points that were all sources, then what you would see is, as you know, maybe you'd have more or less zero flow in the midst of them, but as you went up towards the boundary, you'd start to develop a good bit of flow out. Trying to think, like when people have those irrigation systems, or your lawn gets irrigated by seeping water into it, then that can eventually end up into a flow that you get a whole lot of flow coming out off the sides if you leave the thing on too long. So, so you may have sort of all over the place source or all over the place sink, and that's kind of what's going on with these radial vector fields when we are dealing with well, the two different possibilities for P. If P is such that this turns out to be negative, then generally speaking, stuff must be leaving. There must be a sink somewhere. In fact, that sink is sort of spread out all over space. It's a violation of conservation of matter, in a sense. The matter is disappearing. Actually, if P is smaller than 3, you get the opposite sort of violation of conservation of matter, where the flow is such that if it was actually physical, it would mean matter must be being created somewhere in there. Weird. Maybe not created, but at least added from the outside. I was going to go through this calculation, but after I did it myself, I was like, wow, that is just an algebraic nightmare. So I think I'm not going to ask you to do it either. I just think we're better off if we leave that one be. I did get it eventually, but it took me quite a while. I mean, like half an hour to figure out how to simplify the expression for grad dot f to that. I should at least show you how to get started on it, and then you'll see why it gets really messy. So if you have a vector field F that looks like this, you can re-express that in coordinates as r is just the xyz position, right? And then the length of r raised to the p power, that's square root of x squared plus y squared plus z squared to the p. So what do we get if we do del dotted with that? Well, okay. Let me go ahead and write out what del is. The derivative of partial derivative, the vector of partial derivative operators. I'm going back to writing them in like a fraction. Oh well. I adopted this convention that would have saved some writing, and then I forgot to use it. Okay. I guess we should re-express this so that we don't have it as a vector over a scalar, but incorporate that scalar in the bottom into each component of the vector. So you get x over the square root of x squared plus y squared plus z squared to the p. That's what's in the first coordinate. And then in the second coordinate, it's y over same thing. And I guess you see how z is going to go. I'm just going to say a squiggle there, so you get the idea. And I don't want to do all of these. Each computation is very similar to the others because look how things line up. When we're doing this dot product, it's the partial with respect to x that gets applied to x over the radical to the p. And then it's the partial with respect to y that gets applied to y over the radical p. So if you do one of them, then you can sort of use symmetry to think about how the rest of it goes. So let's, rather than say equals, let's just figure out what is partial with respect to x applied to x over square root of that thing to the p power. Right, so this is where it gets ugly. You have to use the quotient rule here, and it becomes, let's see, everything is over the bottom function squared, so that would be radical of x squared plus y squared plus z squared to the p squared, or in other words, you write to the 2p. And then in the numerator of the quotient rule, you have the bottom times the derivative of the top, which is just square root of x squared plus y squared plus z squared to the p, because the derivative of the top is 1. And then minus, how does it work the other way? Now we need the top times the derivative of the bottom. Right, now remember we're taking the derivative here with respect to x, right? So we're looking at the derivative of this thing that's in the bottom, but the y's and the z's are going to act like constants. All right, we have something to the p power, so we'll have p times that something to the p minus 1 power. The something in there was radical of x squared plus y squared plus z squared plus... Okay, and then we're still taking the derivative of the bottom here. Then you have to multiply by the derivative of the thing in the inside. Now the thing on the inside is the square root of x squared plus y squared plus z squared. So we need to take the derivative of a square root, which has also got something inside of it. So there's one more chain rule to get through. Can I just, I'm sorry, I'm just going to teleport over somewhere else to finish that writing. What's on the end where I just put the star would be 1/2, well, you get square root of x squared plus y squared plus z squared. It's really to the -1 power, so, sorry, -1/2 power. So I'm putting it downstairs as a positive 1/2 power. And then there'll be the derivative of the inside, which is 2x. Well, that's kind of cool. The 2's cancel. That's something at least. Anyway, that's just the x coordinate. You know, the piece that comes from x out of this thing. And while the pieces that come from y and z are similar, the constant having to write over and over again the square root of x squared plus y squared plus z squared is annoying, and it just, yeah. Actually, it might become doable. This is a lesson I always tell students to do, and I didn't think to do it myself. If you've got something that you're writing over and over again that's annoying, just call it something. And then you can, you know, hopefully save a little bit of labor. So, wow, what if I did that as, call the radical of the sum of the squares as u. So what I've got there is u to the p minus x squared u to the p minus 1 divided by, I think that's u to the p minus 1 too. And in the bottom, it's u to the 2p. No, I've forgotten something. There's an x squared that I forgot. There's an x from there, and then there was an x from here. Oh, and there's a p as well. Dang, I'm missing all kinds of pieces. All right, but still, that would be what you get from the x coordinate. The y coordinate would look the same, except it would have y's in it. Whoops. This would have u to the 2p in the bottom, so with this one. And then they'd have u to the p minus u to the p minus 2. Keep running out of space. There's a p and a y squared in there as well. Z squared, sorry, we're at the z level now. You can start to see well, now you can see, in fact, where the 3 comes from. See, u to the p over u to the 2p. Well, that appears in each one of these 3 parts. So we've got 3 times, well, that's 1 over u to the p, isn't it? P minus 2p, yeah, p downstairs. And then there's, what is the rest of these things? Each one has a p minus 2 in it, u to the p minus 2. There's a p in each one of them. We can factor all those things out. And what's left is an x squared plus y squared plus z squared. And I've dropped the bottom of that expression. Which was u to the 2p. Yeah, well, x squared plus y squared plus z squared, that's u squared. So this is just u to the p, and that's u to the 2p. What we've got here is 3 times, well, let's write it this way, 3 minus p over u to the p. Hey, I just sort of accidentally did this a lot better than the first time I tried it. This is what we were after, right? 3 minus p. My u there was just shorthand for square root of the sum of the squares. And that was raised to the p power. So that, in fact, is the divergence of a radial field. You can also write it as 3 minus p times the length of r, length of the position vector to the p power. That was fun. Well, another sort of broad category of vector fields that people play with are called rotational fields. So in a rotational field, your position, you just take the cross product of some fixed vector with your position vector. I just want to check something here. I think I want to make sure I do it in the right order. Yeah, because you'll introduce a sign error if you go the wrong way. You take a fixed vector A crossed with your position vector. So an example of that, how about if A was equal to 0, 0, 1? Of course, R is the position vector in general, so it's x, y, z in the 3 positions of the vector. So if we do that cross product computation, well, what do we get? When we go to I, it's 0 times z minus y. So in the I component, it's minus y. When we go to do j, it's 1 times x minus 0 times z, so that's just x. And when you go k, you get a 0 in both parts of the little x that you do there, so you get 0. And that's actually a rotational field that we've played with multiple times, right? If you switch the variables and then put a minus sign on one of them, you get a vector field that looks like rotation. So that's an example of it. But the thing is, that's cool is you can make this constant vector pretty much anything, and it becomes the axis of rotation for the field, which is neat. If you want to get a bunch of vectors that are swirling around a line that's on some diagonal, then you just choose the vector in the direction of that diagonal line and get the rotation of it. So, one of the things that's cool about this kind of a rotational vector field is what its curl tells you. So you might not have the vector field, you might not have it in the form A cross R, and they may have already told you what that computation is. But when you take the curl of it, whatever it is, you pull A right back out. It's kind of neat. Let's watch it. It actually comes out with a scale factor on it, but still, it's more or less the right thing. Let's just do this with an example, I suppose. Suppose A is the vector 1, 2, 1. Then a field that's got by looking at A cross R we have to do that cross product calculation again. So A was 1, 2, 1, R is X, Y, Z. What does that come out to be? In the I coordinate, we'll have, man, my writing is sloppy. That's a Z on the end. 2 times Z minus Y, so 2Z minus Y is the X coordinate. And when we go to do J, it's going to be 1 times X, so it's X minus Z in the Y coordinate. And for K, it's Y minus 2X. Now suppose you didn't know where they came from, right? They hadn't told you A up front. You have this vector field. And somebody says it's a rotational field. You try to compute what its curl is. Which means you do the del operator crossed with the field. So, I guess I should write it out. No, maybe I shouldn't. Let's just start throwing things into the computation that we would do to do the cross product here. I'm going to spread I, J, and K out a bit because we've got these longer things to fill in there. The del operator, I remembered to do the shorthand version this time. All right, 2Z minus Y there. X minus Z in the middle, and Y minus 2X on the end. So what does that cross product calculation get us? It's a vector again, right? And in the I coordinate, we'll have partial Y of that expression, which is 1, minus partial Z of this expression, which is minus 1. So we get 0. What? Partial Y, that is 1, minus 1. That's 2. Sorry. Messed that up. I knew it wasn't going to, because I knew it was related to A. All right, what's in the Y coordinate? That's when we cover up J and X the other things. Partial Z of this one gets me a 2, and partial X of that one, that's a minus 2. But that one's subtracted, so that's 2 minus minus 2, or 4. And then lastly, the K coordinate, it's a partial X gets us a 1, minus partial Y gets a minus, yeah, that's another 2. And notice that that's equal to 2 times the axis that A stands for axis, because this is it actually is the axis around which the rotation kind of flows if you build one of these. Well, that's fun stuff. Lastly, we just got two theorems to get through at the end of this section. One of them, theorem 17.11. I guess I should erase. So theorem 17.11, it's on page 1141 if you want to go look it up. It says the curl of a conservative field is 0. And actually that's the way you hear people say it. But one's speech can't emphasize the fact that, that 0 on the end is not really a 0. What you need to remember, of course, is that if you do a curl, you're doing a vector cross product. And the answer out of a vector cross product is always a vector. So this thing needs a hat. The curl of a conservative field is a 0 vector everywhere. So it's really kind of odd. The curl is something you can compute at any position in the vector field, and all those positions are going to come out zeros if you've got a conservative field. So how do we prove this? Well, I think it's worth going into a little bit because it's just a computation. If you've got a field F that's a conservative field, that means it is somebody's gradient. So if you have a conservative field, there must be a scalar function, a potential function for which F is the gradient. I guess that needs a comma. Such that, well, I didn't need a period there yet, such that what's going to happen is that if you take the gradient of phi, you'll get F. Or that F is equal to del times phi. I started to use a little F. I don't know why. Del times phi. All right, so when we ask about the curl of this conservative field, we can also ask about the curl of del dot phi. So I just want us to think about what happens when you do del crossed with del times a function. That's a great line, by the way, in an argument. Just invite your reader to consider something. I think it's a I enjoy moments like that. Just think about this idea. And then I'm going to lead you through what we want to see when we consider that guy. What is it that we expect to happen? Well, del crossed with del times phi is equal to, let's just set it up. It's the partial derivatives in that vector. I'm just writing out what del is. I forgot to use my shorthand again. Oh well. Crossed with, when we take the gradient of the vector function, or of the scalar function, we get a vector whose components are the x, y, and z partials of that phi. So you get phi sub x, phi sub y, and phi sub z. All right, so let's see about computing that cross product. I, J, and K. I better stick the shorthandy versions in here because the other ones were too big. And then we have phi sub x, phi sub y, and phi sub z. Maybe I can write that just next to it. What do you get in the x coordinate? That'll be the y partial of phi sub z. That is phi sub zy. Minus the z partial of phi sub y. That is phi sub yz. In the y slot, you were going to get the z partial of phi sub x, that's phi sub xz, minus, what's the other one? The x partial of phi sub z, that's phi sub zx. And don't have room for it in the line, so we'll finish it off here. When we do the k component, we get partial with respect to x of phi sub y, so phi sub yx, and then subtracting, we'll get partial with respect to y of phi sub x. That's phi sub xy. Do you see why all of these are 0? These guys are mixed partials in the two possible orders, z sub y, zy and yz, but those things are equal to each other, so that's 0. And same thing here, these two are 0, not 0, but equals and thus 0. And yeah, there. That's just a 0 vector. So the reason that the curl of a scalar, the gradient of a scalar potential comes out 0 really comes down to Clairaut's theorem again, that the mixed partials are equal. There is a proviso on here that the mixed partials, or everything has to be continuous on the domain you're looking at. But I believe that's the case already if we're talking about F being a conservative field. So that's 1711. 1712 is another one that says, in certain ways, if you put these del operators together, you get a 0. And this one, it's the divergence of a curl. We just took the curl of a gradient and got 0. The divergence of a curl is also 0. This is on the same page as the previous one. I forgot what I wrote down. Well, not so hard to find in this section. So it doesn't matter what vector field you start with. If you take the curl of it, do del cross the field, and then try to figure out what divergence it has, you will find that it has none. Now, last time I wrote down 0, and then I said, well, actually, that's not really 0, but this one really is 0, because when we take the divergence, it's del dotted with a vector. Dot products become, one-dimensional or scalars. So that's a scalar 0, not a vector 0, like in the last theorem. And the proof of this is actually going to come down to Clairaut's theorem too. So suppose F has F, G, and H as its coordinates. Each of those is a function of position in space. So F of x, y, z, G of x, y, z, H of x, y, z, really. Then the curl of that, del crossed with F, is, let's just write it into the determinant version of things right away. We'll need the partial with respect to x, y, and z. Is the second row, and F's component functions F, G, and H is the third row. And so what do we get out of this? When we're doing the I partial, it's H sub y minus G sub z. The J component, it's going to be F sub z minus H sub x. And last one, the K component, it's G sub x minus F sub y. We've seen that guy before, haven't we? All right, so that's what del cross F is. Now let's see what happens if we take the divergence of that. So that is del dotted with del cross F. I guess need parentheses to explain that. Is take the x partial of the x coordinate. So you are going to get h sub yx minus g sub zx. What am I doing? I'm such a dope. I actually even talked to you guys about how this is going to turn out to be a scalar. And I started to write vector braces here. Bad boy. Anyway, is that the right thing? We're going to be taking, the del operator, which has partial x, partial y, partial z in it, times this vector. So first those guys get x derivatives, then the next guys get y derivatives. So it's fzy minus hxy, and then finally the last guys get z derivatives, so that minus gxz minus fyz. Right, now this isn't quite as obvious that it's 0, but the mixed partials are in here again, and if you notice, they pair up. H sub yx and h sub xy are both in here, and one's negative. So what happens when you subtract two equal things? You get 0. G sub zx and g sub xz, those guys together, one's negative, the other's positive, 0 again. And I probably made it too ugly to try to fit it in, but see how it's plus f sub zy and minus f sub yz, 0. A scalar 0. So we've just had two theorems about how you can kind of combine del and del dot something and del cross something. That is, these things are sort of shorthands where you can combine gradients, divergences, and curl. Which I have to say, there's a really tremendously good book on advanced calculus called Divergence and Curl and all that, which is, we've got the title of the book staring at us right here. Yeah, strong recommendation if you're finding all this stuff interesting and want to pursue it a little bit more. Michael Spivak, Divergence and Curl. It's a great. A short little thing, but it really gets you to think more deeply about this stuff. Anyway, what we just did was say, for instance, if we took the curl of something and took the divergence of a curl, we got 0. And then previous to that, we took a gradient of something, and then we took the curl of that, and we got a 0 vector. But what other ways can we combine these things? And actually, it's sort of intriguing that there are certain things that you can't do. For instance, what if I tried to take the gradient of something that was a curl? What would that be? Well, it's just undefined, because think about this, what sort of shapes things have. This is going to be a vector, right? Does the gradient, or does the del operator multiply on a vector? So if the little multiplication, that little tiny dot that I write down there was multiplying, not dot product. So can we multiply a scalar, or sorry, can we multiply a vector times a vector? No, that doesn't work. So to do gradient of something, I have to have a scalar thing, and cross product's not. Could I do, let me make sure I get the right other one. Could I do the cross product of a dot? That is, could I do del crossed with del dot, a vector field? And that's a dot product. See how much bigger and darker that dot is than this dot? I'm just kidding. But that has to be a dot product there, because I've written the del symbol in a vector field, and we've just seen that if you had put del next to a vector, you can't mean multiplying. Okay, you must mean dot product. So can we do this? No again. In fact, I never wrote it down. I should have said it, but didn't write it down. That's undefined because the operations just are undefined. And this is undefined as well. What's the problem here? Once I do del dot with f, I've got a scalar. And now I'm trying to cross a vector and a scalar. Not allowed. All right, so one thing that is left that you can do is this. You can take the gradient wait a second, how do I want to say that? Del dot del u. Sorry, yeah, it's not the gradient, it's rather the divergence. Del dot L f for a little function f. So watch out. The two kinds of multiplying are both in here. That is the del operator times the scalar function f. This bigger dot is the dot product of it, and I think the implied order of operation is that. So what is that thing? You can do it, and let's see what it gets you. That'll be the del operator dotted with, well, the gradient of f, so f sub x, f sub y, f sub z. And then what does the del dotted with this vector do? It takes the x derivative of that one, the y derivative of that one, and the z derivative of that one, and it adds them all up. And that turns out to be a really important thing in physics. It's called the Laplacian. I don't have room to write it here, but here, Laplacian. I can't spell it either. The man's name ends in an E there, but I think the way this thing that comes out, that is named after him, is spelled is like that. It's part of a thing called the heat equation. It's used to model anything that's a sort of a diffusive phenomenon, but many other things as well, vibrational things, and I don't know, lots to it. Actually, you know, in 26 dimensions, it's the heart of string theory. So we're not going to play with the Laplacian anymore. I just sort of, while we're at this moment, I was like, well, I kind of showed them that one last thing. And that is a final element of coolness for today. So we're done.